Hello students, welcome back to Rama Teaches You. Today we are going to do IB Physics. IB Physics theme D, and in theme D part A we have already done the gravitational field. Okay, we have done the gravitational field. Now we are moving on towards electric and magnetic fields. Okay, electric and magnetic fields. So we have already studied that what an electric field is, right? What is a gravitational field? A gravitational field is a force field around a particle of a particular mass in which if we place another mass it experiences a force. That is what we call a field. Right? Huh? Fields are usually produced by forces that are non-contact in nature. Right? So, how does a non-contact force exist? A non-contact force exists because of the presence of a field around that force. Okay, around that object that is causing the force, there is a field around it. And if we come into that field, what will happen? The object will experience a force. Understood, Akshay? Put it up. Okay, so in this chapter, what are we going to do? In this chapter, we are going to discuss from the basics of what electrical charges are and the direction of forces between them. We are going to understand Coulomb's law. We are going to understand the conservation of an electric charge, Millikan's oil drop experiment, the transfer of electric charge using friction, electrostatic induction, and by contact. And then we are going to understand about electric field lines, electric field intensity and electric field strength, and finally the magnetic field lines. Okay, let's start. Okay, so introduction. Electromagnetism is an effect observed when charge moves in a circuit. Okay, electromagnetism is an effect when a charge moves in a circuit. And how does the charge move in a circuit? Usually what happens is when we apply a certain supply, okay, and a certain potential in the circuit, what happens? The electrons in that circuit start to move, right? They start to move from a higher negative potential to a lower negative potential. And as we all know, the conventional current moves from a positive terminal to the negative terminal. Okay, the electric current leads to the appearance of magnetic field, but it was not the observation of magnetism arising from the electric current that began the ancient study of magnetism. Early navigators knew that some rocks are magnetic and that the rocks could move to indicate the direction of magnetic field. Okay, they basically there was a shepherd. There was a shepherd who had a stick, and at the end of the stick there was a small iron piece. And when he was herding the sheep, he observed that when he was traveling, his stick was getting stuck to one particular rock. Okay, and he didn't know what was happening at that time. So what was happening there was the rock was naturally magnetic in nature. The rock was producing its own magnetic field. Okay, and that magnetic field was attracting the iron in his stick, which was allowing it to get stuck to the rock. Okay, however, the true origins of the magnetic field remains obscure for many centuries. Only comparatively recently has our knowledge of the microscopic aspect of materials allowed us to understand how magnetism arises. Okay, now, first things first. So, our first topic is static electricity or electrostatics. Okay, now, if a charge remains stationary at a particular point, the study of such a charge is called electrostatics. But if a charge starts to move, we call it electrodynamics. If a charge is at rest, if a charge is at rest, it will not produce any current. No current will be produced if the charge is at rest. Okay, so in topic B5, the origin of electric current was explained in terms of free charges or electrons. Now, the metals are able to conduct electricity because of the presence of free electrons. These free electrons allowed are what allow the current to flow freely through the conductor, and the absence of free electrons in an insulator makes it a non-conductor of electricity, right? It makes it a non-conductor of electricity. In the context of electrostatics, static electrons are added to or removed from an object. Okay, they are either added to an object or they are removed from an object. We all know that what is an electron? An electron is a negatively charged particle. Am I right? An electron is a negatively charged particle which revolves around the outer shell of the nucleus. The electron is a negatively charged particle which revolves around the outer uh, outside the nucleus in various different shells, right, on energy levels. Now, we cannot physically take out the proton from the nucleus. It is impossible for common everyday objects for their protons to get lost. So what happens? Usually an item either gains an electron or loses an electron. If it gains an electron, what happens? The number of protons is less than the number of electrons, therefore it becomes negatively charged. If it loses an electron, then the number of protons is greater than the number of electrons, therefore it becomes positively charged. This is how we have charged particles. Okay, the gain and the loss of electrons gives rise to charged particles. Okay. Okay, now experiments show that a positively charged object is attracted to objects with a negative charge but repelled by a positive charge. This is because we have learned it from a very young age that like charges repel each other and unlike charges attract each other. For example, a positive and a positive will always repel each other, and positive and the negative will always attract each other. We are going to learn more about it in this class, how it is attracting each other, because a positive charge will always emit the electric field in the outward direction, whereas a negative charge will attract all the field lines towards it. Okay, that is the reason why there is a force of attraction also. Okay, experiments show that positive charge is attracted to other objects with a negative charge but repelled by a positive charge. Simple electrostatic effects are due to the movement of negatively charged electrons. Positive charge arises from the presence of ions in a substance. An object with no observable charge has an exact balance of electrons and the positively charged protons. If you have the same number of electrons and the same number of protons, then the object is not charged. The object is said to be neutral. The object is said to be neutral. Okay, so figure 2a and 2b. Figure 2a and 2b show the interaction between opposite charges like the and like charges. They can attract. They can be an attraction between charges and uncharged objects due to charge separation. Now, again, here's a very interesting. So, two unlike charges can attract each other, right? A like charge, sorry, any charge and a neutral object can also attract each other. I'll explain to you how. Okay, so we all know that if you have a positive charge here and a positive charge here, this positive charge will most probably try to shove this positive charge in this direction, and this will shove this positive charge in the other direction. Okay, and we also know that a positive charge and a negative charge, what will they do? They will try to attract each other. They will try to attract each other. Now, in our case, what is going to happen? In our case, when we have a positive charge and a neutral charge, what happens is this positive charge, when it is brought near a neutral charge, there is something known as induction, electromagnetic induction. Okay, so what happens here is that this object starts to get polarized. That is, there are electrons present on the surface of this object. We can agree that there are electrons present in the surface of the object. Now what is happening to these electrons is that these electrons are getting attracted towards the positive charge, and because these electrons came from all over the body, what happens? There is a certain region in the object where there is a concentration of positive charge. So you are basically polarizing the object. You are polarizing the object in such a way that one side of the object becomes positive charge and the other side of the object becomes negative charge. And this leads to what? This leads to an attraction between the positive of the positively charged object and the negatively charged side of the neutral particle. If you remove this charge, if you remove this charge away from this object, the electrons will get redistributed again and the object will become neutral again. Okay, so this is what's happening in this case. Okay, so there can be attraction between a charged and an uncharged object due to charge separation in the uncharged object. So you have created a charge separation by bringing a charged particle next to a neutral particle. Okay, in figure 2c, the free electrons in the uncharged sphere A are repelled by the negative sphere B. They move away to the other side of the sphere A. They move towards the other side, due to which what happens, you have polarized the whole charge. Okay, these positive are closer to sphere B than that of the negative charges. The electric forces increases with the decreasing distance, and so the overall force of the sphere A is towards sphere B. Okay, the overall, this see, basically this was the negatively charged object. You brought it next to a neutral object, due to which what happened, most of the positive charges got concentrated here. The electrons that were present on the surface got repelled because of this is a new negative charge. The electrons on the surface of this object got repelled towards the other direction. Therefore, you were able to get a net positive charge here and a net negative charge here. Therefore, this positive charge is attracted towards this charge. Understood? Okay. Now, when explaining the effects described here, always describe negative charge in terms of surplus of electrons and positive charge in terms of deficiency or lack of electrons. Understood? Now, what is a conservation of charge mean? Okay. Now, during the process of electricity move generation, either through electrostatic or electrodynamic generation. Okay, you can neither create an electron nor lose an electron. Okay, you can neither create an electron nor destroy or lose an electron. All of this, all you are doing is transferring electron from one place to another. You are just a transporter. Okay, there are various means of transporting the electron, like you can rub a scale on your head, or you can use friction with other with a piece of cloth and this thing, glass rod. You can create charges. You can create charges by transfer of electrons from one place to another, but you cannot destroy an electron. Okay, so charge carriers in a single conductor must move in and out of the conductor at equal rates. Okay, they must move in and out of the conductor at equal rates. Now, I'll explain this to you what is happening. Now, imagine that you are having a river. You have a river, okay, a river with various junctions. Now, this is the Ganga River. Okay, this is the Ganga River in which the water is flowing like this. Okay, and then we all know it is a massive river. Right? Ganga is a very massive river. It has a lot of tributaries all across India, and it is basically important for irrigating the whole northern part of India. Right now, let's observe that it has two tributaries like this. Okay, it has two tributaries. The Ganga River is bifurcating into two of its tributaries. Now, think about this, Akshay. If the water is traveling like this, if the water is traveling like this, then the amount of water that is flowing here, should it be equal to the amount of water flowing here plus here? Right. Basically, if 100 liters of water is flowing through this particular area in 1 second, then this plus this should also be equal to 100 liters per second, right? Yeah, so because of this, what happens, you're not creating water, right? In the junction, you're not creating any water. Similarly, in the case of current, In the case of current, the amount of current that is entering a junction should be equal to the amount of current that is exiting the junction. The amount of what is current? What is the definition of current, Akshay? No, 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 no. It is the rate of flow of electrons. Charge upon time. It is known as the rate of flow of electrons. Okay, so basically, what is happening here? There are a few electrons that are entering the junction, and there are a few electrons that are leaving the junction. According to conservation of charge, the amount of electrons entering the junction should always be equal to the amount of electrons that are exiting or leaving the junction. Understood? Okay. That's what's written here. So charge carriers in a single conductor must move in and out of the conductor at equal rates. The same applies at the junction. Figure 3 shows a junction with three incoming currents and two outgoing currents. Current splits at the junction, but the number of electrons moving in and out are in the same time at the same second. Okay, so the amount of current that was entering in, that is I1 plus I2 plus I3, should be equal to the amount of current that is going out, which is equal to I4 plus I5. Clear? Okay, now, which means that the sum of the current flowing into the junction should be equal to the sum of the current that is flowing out of the junction. This is a consequence of conservation of charge. Understood? This is what we call conservation of charge. Charge can neither be created nor be destroyed as it is flowing across a junction. Across a junction, the amount of charge that is flowing will always be conserved. It will always be conserved. Understood? Okay, next. This important rule was first spotted by Gustav Kirchhoff. Okay, now the Kirchhoff is one of the scientists who basically gave us a lot of laws. We have the Kirchhoff's junction rule, and we have the other Kirchhoff's loop law. Okay, and we have learned about this in electric current. In electric current, what did we learn? The one simple line that basically gives the Kirchhoff's law a lot of significance is that across a junction, the amount of current entering should be equal to the amount of current leaving. And number two, what was it? The potential supplied to the circuit should be equal to the potential dropped across the circuit. Okay, potential supply to the circuit. If you are supplying 10 volts into a circuit with the help of a battery, then this 10 volts must be dropped across the circuit. The 10 volts must be dropped across the circuit, right? Okay, okay, no problem, no problem, no problem. Okay, we'll learn about this more in later classes. Now, this important rule was first quoted by Gustavo Kirchhoff in 1845. He devised another electrical conservation rule, conservation of energy. In a closed electrical circuit, the energy being converted into electrical energy must be equal to the energy transferred from the electrical to the internal by a potential difference sink. So basically, in very very simple terms, he is saying the amount of voltage supplied in should be equal to the amount of voltage drop. For example, let's look at a simple example. Okay, now imagine you have a circuit like this. This is a 10 volts battery. You have one resistor like this, and you have another resistor like this. Okay, this is 10 volts, and let's call it 4 ohms, and let's call it 6 ohms. Okay, let's call it 4 ohms and 6 ohms. Now, what is the net resistance in the circuit? 10 ohms, because both the resistors are in series. So, R net is equal to 10 ohms, right? R net becomes equal to 10 ohms. Now, what is the current flowing through the circuit? Voltage upon resistance. What is the voltage? 1 ampere, exactly. Now, what is the voltage drop across this resistor? Now, imagine that there is a 1 ampere current flowing through the resistor. So, voltage drop across this resistor will be how much? V is equal to IR is equal to 4 volts. The amount of voltage dropped across the 6 ohm resistor will be how much? 6 volts, right? The voltage across, see, 6 into 1, the current flowing through the circuit is I. I is equal to 1 ampere. So, there will be 4 volts dropped here and 6 volts dropped here. How much supply were we giving? We were giving 10 volts supply. 4 got dropped here, 6 got dropped here. So the amount of voltage supplied in should be equal to the amount of voltage dropped across the circuit. This is Kirchhoff's loop law. Understood? Okay, let's move. Now, now we know that in order to make an object, in order to make an object charged, you need a transfer of charge. Some electrons have to get transferred from one object to the other. Without that, you cannot create charge. It's highly clear, right? Now, what's the various ways through which this can be done? There are three methods through which charge can be transferred between objects. The first one is what? Charge transferred by friction. This is the game we used to play in when we were young, right? We used to have a dry scale, a plastic scale. We used to rub it in our hair, dry hair, and then that scale was to be used to pick up small bits of paper. You can even try this at home. Okay, you rub it like this. The electrons on the scale, on the surface of the scale, will get transferred to our hair. So our hair will become partially negatively charged. The scale will become partially positively charged, and then when you have bits of paper on the ground, very tiny bits of paper, they are neutral. They are neutral in nature. So basically, if you bring the scale next to these paper particles, what will happen? They will induce a negative and a positive charge. You are inducing a negative charge. Remember this, right? So when you bring a charged particle to a neutral object, what happens? You are inducing a charge. You are inducing a charge, and this causes what? Opposite charges. If the scale is positive, then the portion of the paper nearer to the scale will become negatively charged. There will be an attraction between the scale and the paper. That's it. That's what I'm talking about. Next. So, rub a perplex rod. Okay, perspex. Perspex rod with a cloth, and both objects become charged by friction. This is known as the triboelectric effect. Okay, this is known as the triboelectric effect. The perplex loses electrons and gains an overall positive charge. The electrons that are transferred, okay, the electrons that are transferred to the silk give it an overall negative charge. So the perplex rod, right? PERS, perspex. Perspex rod becomes positively charged because of the loss of electrons, and the silk cloth becomes negatively charged because of the overall gain of electrons. And exactly. Now the electrons that are transferred to the silk give it an overall negative charge. Notice that electrons are not lost in these transfers. If 1000 electrons are removed from the rod, 1000 electrons are gained by the cloth. Okay, now again, charge is conserved here. Two materials charged by friction end up with opposite charges. Okay, so if you are using friction to create a charge, then both the objects will have opposite polarities. One will become positive, the other will become negative. Understood? If you rub a glass rod with a silk cloth, the glass rod becomes positive and a silk cloth becomes negative. If you rub a plastic rod with the wool cloth, what happens? The plastic rod becomes negative, the wool cloth becomes positive. Okay, so always one, you will have two different charges always produced when friction is taking place. Understood? Two materials charged by friction end up with opposite charges. This is the main part of this section. Now, in charging by friction, as the silk and the glass rod are rubbed together, the atoms on the surface of both materials are in close contact. Initially, the electron cloud surrounding the atom surface does not interact. Okay, initially the electrons are not interacting with anybody. But what happens? However, because of an external force being applied, you are rubbing the scale with a cloth. What happens? The energy barriers between the electron clouds are modified and electrons transfer from one material to the other. So when you were rubbing the perspex rod with the silk cloth, what were you trying to do? You were trying to give the energy to the electrons in the perspex rod, so that they would energize themselves and move towards and become free. They would become free from the perspex rod, and then they will eventually get transferred to the silk cloth. Okay. Now, however, because an external force is being applied, the energy barriers between the electron clouds are modified, and the electron transfers from one material to the other. When the force is removed, what happens when the force is removed? The energy barriers return to their original state, and the electrons remain in their new location. Okay, once the rubbing is done, you are no longer providing it with any more energy. So the electrons that got transferred from the glass rod to the silk cloth will remain in the silk cloth, and the glass rod will have lost electrons. Okay, the glass rod would have lost electrons, thus making it a positive charge and making the silk cloth a negative charge. Okay, so who was providing the electrons energy for this passage? We were providing it energy by using the friction. Now, table 1 shows some materials in the triboelectric series, which show the relative strength of materials with respect to their charging. When a material is rubbed against a material on the list, the material closer to the top is likely to become positive, while the lower materials become negative. So, look at this. See, if glass is rubbed with silk, glass becomes positive, silk becomes negative. If leather is rubbed with ebonite, leather will become positive, ebonite will become negative. Okay. So if amber is rubbed with plastic wrap, amber will become positive and the plastic wrap will end up being negative. The success of the plastic wrap cling film is due to several factors, including its elasticity and the fact that it becomes charged by friction as it is pulled off across the roll. This means that it will cling effectively to neutral objects that have some free electrons. Now, when you are removing the plastic wrap from the foil, from the roll, what ends up happening? The plastic wrap becomes negatively charged. The plastic wrap becomes it becomes negatively charged. Therefore, what happens? It is able to attract itself. It is able to attach itself to the neutral objects, just like a magnet would do. Okay, your fridge magnet is basically magnetic in nature, but your fridge is not magnetic in nature. But what happens? The magnet is able to stick well to the fridge, right? Similarly, you have a cling, you have a clean floor. That plastic wrap is what? Plastic wrap is negatively charged. Okay, it is negatively charged. So it is a charged body being placed on a neutral bowl, whichever food you want to preserve. It is placed on a neutral bowl. So what happens? Along with its elasticity, the electrons in that plastic wrap get attracted to the now induced positive charge of the bowl. Due to which, what happens? It will cling itself much more tighter to the bowl. Okay. Now, charge transfer by contact. A simple method to charge an object is to put one charged object in contact with an uncharged object. Some of the electrons are transferred from one to the other, leaving the initially charged object with a reduced overall charge. The uncharged object is no longer neutral but gains charge with the same sign as that of the original object. Understood? This is known as induction. This is how we are able to lift pieces of paper from the ground. We are able to lift pieces of paper from the ground because the charged scale is able to induce a charge. The charged scale is able to induce a charge on the pieces of paper. It is able to polarize a charge on the piece of paper, allowing it to get attracted. Understood? Okay, next. Materials charged by contact end up with the same sign of charge. They end up having the same charge. Now look at this. Now the third is charge by electrostatic induction. This is the like the basically um, it is also induction only, but here what happens is we are trying to make both of them like we are trying to create. See, in induction what happens when you bring a charged particle next to a neutral particle, okay, it will induce electrons on one, it will basically split the whole object into two sides, right? One with the electrons concentrated on one side and the other where the positive charge is concentrated. Now think about this. See, you brought a negatively charged rod next to a this thing, what do you say, a conductor next to a this thing. Now this is an insulating stand. Okay, okay, this is a conducting sphere and this is an insulating stand. So what happens, because of this negative charge in the rod, the electrons that are present on the surface of this conducting sphere, what happened, they started moving in the opposite direction because they were being repelled by the electrons in this rod. Okay, now think about this. You are connecting the conducting sphere to the ground by a conducting wire. Now what happens? The earth is the ultimate charge acceptor. Okay, the earth is the ultimate charge acceptor. What happens? Now these electrons, now because they have a contact with the earth, the electrons, because they have a contact with the earth, they are able to travel through the wire towards the earth, thus leaving an overall positive charge on the sphere. Now if you remove the charged rod, now if you remove the charged rod, as in the case of the third figure, what happens? There is an excess of and a deficiency in negative charge, right? So what happened here? you were able to create you were able to create an overall positive charge. You were able to create an overall positive charge by transferring the excess electrons towards the earth. Okay, now this will be positively charged for a long time, until unless if it is isolated from the surrounding. If it is isolated from the surrounding, it is already isolated from the ground with the help of an insulating sand. If it is isolated from the surrounding, what will happen? This will have a positive charge for a very long time. Clear? Next. Now, the process shown in figure 5, a charged rod is brought to a neutral neutral object, in this case a conducting metal sphere, on an insulating stand. The rod is negatively charged and this repels some of the free electrons to the bottom of the sphere. There is charge separation and the sphere is still neutral because the charge remains balanced overall. You are having an overall balanced charge. Now then there is a charge separation, balanced charge. The concept of electric potential and how it applies to charge is explained later in this chapter. Now, the sphere is now earthed. Earthed means what? What do we mean by earthed? It means we are connecting the object physically. We are physically connecting the object to the ground. How did we do this in the example? We did this in the example by connecting the object with the earth. We did this by connecting the object with the earth, right? Now, the sphere is now earth by connecting a conductor between the ground and the sphere. The sphere now has zero potential. Some of the free electrons are repelled by the rod, move through its connections and flow down to the earth. So the earth has now absorbed the excess electrons. The earth has now absorbed the excess electrons, leaving behind only positive charge on the sphere. Okay, now move. Okay, the loss of electrons leave the sphere with an overall positive charge. When the rod and earth connection is removed, the free electrons in the sphere will be rearranging themselves to give an even distribution of positive charge on the sphere. Notice that when the charged rod is removed, there is now a force of attraction between it and the sphere because they now have opposite signs. Okay, so in this photo, you have a negatively charged rod and a positively charged sphere. So, because they are two, there exists two charge parts, two charges with opposite signs. They will obviously now attract each other, right? They will obviously try to attract each other. Next, when the rod and the earth connection is removed, the free electrons in the sphere rearranges themselves to give an even distribution of positive charge on the sphere. Notice that when the charged rod is removed, there is now a force of attraction between it and the sphere because they now have opposite signs. Work must be done to remove the rod. The electric potential of the sphere has now changed. The potential that the sphere had in the beginning was zero because it was neutral in nature. But because you have now induced an overall positive charge in the sphere, to remove that negatively charged rod, you have to do some work because there is attraction happening, right? Think about this. There is a positive charge, there is a negative charge. They are attracting each other due to the Coulombic forces of attraction. Now, to remove them apart, you have to do some work, right? You have to do some work. Did you understand this logic? You have to do some work. Why do you have to do some work? You understood, right? Exactly. Next, let's look at this question. A positive charged rod is brought up to an initially neutral conducting sphere. You initially had a neutral conducting sphere. The sphere is grounded and the rod does not make contact with the sphere. Okay? The sphere is grounded, the rod does not actually touch the sphere. As the rod is moved towards the sphere, there is a short pulse of electric current between the sphere and the ground. Explain the direction of its conventional current. Now, what was happening here? Okay, what was happening here was when you were bringing this positively charged rod to this conducting sphere, the electrons that were present in the sphere got concentrated here. The positive charge was basically concentrated on this side. Okay, so the positive charge was concentrated on this side of the sphere. Then electrons were concentrated on this side of the sphere. So, Earth being a ground, it can either supply electrons or absorb electrons. So, what happens? Because there is positive charge concentrated on this side of the sphere, it started taking in electrons. It started taking in electrons from the ground, making this neutral. This side of positive charge became neutral. Now, what ended up happening? You were only left with electrons here. Okay, you are only left with electrons here. Now the rod attracts free electrons in the sphere, causing a flow of electrons from the ground to the sphere. The conventional current is always opposite to the flow of electrons. In current electricity we have done this. The conventional current is always opposite to the flow of electrons. So if the electrons are moving from the negative terminal to the positive terminal in a circuit, then the conventional current will flow from exactly the positive to the negative terminal. The ground is now removed. State the sign of the charge induced on the sphere. What will be the charge induced on the sphere? An overall negative charge, right? There will be an overall negative charge in the sphere because you have neutralized the excess positive charge. You have neutralized the positive charge that was created. Okay, how did see basically what did you do? You brought the positively charged rod next to the sphere, due to which what happened? The electrons or in the on the surface of the sphere all got attracted towards one side. So you are left with a positive charge on the other side. You're left with a positive charge on the other side. Now, this positive charge attracted electrons from the ground. Okay, so due to which what happened? One positive charge and one negative charge, when they came next to each other, they neutralized themselves. Another positive charge and another negative charge again came and neutralized themselves. So all this positive charge got eliminated. So you were left with what? Only negative charges on the sphere. Okay, you were only left with negative charges on the sphere. So your sphere became an overall negative charge. Understood? Okay. No, 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 no. It is a reservoir of charge. It is a reservoir of charge. It can provide you electrons or it can be a pathway for the removal of electrons. If it is providing you electrons, what happens? If it is providing you electrons, then basically you can say that Earth has a negative potential. If it is absorbing electrons, you can say that Earth has a positive potential. But we say that Earth is grounded. Earth has zero potential. So it has the ability to absorb electrons or give electrons. Clear? Okay. So are you late for the school now? Do you have time? How much? Okay. Sure. Force between charged objects. Okay. How does the force between the charged objects work? In 1785, Charles Augustin de Coulomb reported his series reported his series of investigations into the effects of force from charged objects. He found experimentally that the force between 2 point charges a distance r apart is directly proportional to 1 upon r square. 1 upon r square means what? There is a certain force existing between two charged particles, and that force basically is increasing as the distance between the charged particles is decreasing. Okay, and how is it decreasing? It is decreasing inversely to its square of the distance. Okay, he observed that the force is decreasing when the distance between the charges is decreasing. Force is increasing when the distance between the charges is decreasing. This confirmed earlier theories by Daniel Bernoulli, Alexandro Volta, Joseph Priestley, and others. Like Newton's law of gravitation, this is also an inverse square law. Inverse square law means what? Your distance, if your force, the force that is existing between two objects is inversely proportional to the square of the distance between them, then we say that they follow the inverse square rule. Since, like we said, the force between two masses is what? Gm1 m2 upon r square, right? The force between two masses is gm1 m2 upon r square, and we know that if we decrease the distance between the two objects by half, then the force becomes 4 times. If we decrease the distance between the two objects by a third, then what happens? That the force becomes 9 times. So this is known as the inverse square law. Clear? Inverse square law. Any doubts in inverse square law? Okay. So we're not going to do this. Yeah. Later experiments confirmed that the force is directly proportional. It is directly proportional to the product of the size of the point charged is Q1 and Q2. So, if there are two objects, Q1 and two objects having a charge of Q1 and Q2 separated by a distance r, then we can say that the force between the two objects is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Okay, so we can say that Force is directly proportional to Q1 Q2 upon R square. Now, when we try to take out the proportionality constant, when we try to take out the proportionality, we have to introduce a constant which is known as what? The force constant. Okay, so basically it becomes the magnitude of force F between 2 point charges of q1 and q2 separated by a distance r is called kq1 q2 upon r square, where k is called the Coulomb's constant. It is known as the Coulomb's constant, and for all intents and purposes we are going to use it as 9 into 10 to the power 9 Newton meter square per kg square. I'll explain how we got the Newton meter square per kg square. So, what is the SI unit of force, Drupat? Sorry, what is the SI unit of force, Akshay? Newtons, right? Newtons. Newtons. So, K Q1 Q2 upon R square. What is the SI unit of charge? Coulombs. So, at the top you are having Coulomb square, right? At the bottom you are having meter square, but you want an overall unit should be in newtons, right? So you need to have Newton meter square per kg squared in order to cut, sorry, Newton meter square plus upon Coulomb square. I accidentally wrote down the value of G, capital G. So these will get cut off. So you will be left with newtons. This is how you get the SI unit, Newton meter square plus kg square upon kg square. Okay? Sorry, Newton meter square upon Coulomb square. Okay? See, that is the only way you will get the overall unit to be in newtons, right? Because you want the overall value to be in newtons. Understood? Okay, next. Now, the separation does not appear to give the direction of force between the charge, does not appear to give the direction of force between the charged objects. Forces are vectors, but the quantities, charges, and distance squared are scalar. There are mathematical ways to cope with this, but for point charges, the equation gives an excellent clue when the signs of the charges are included. Okay, so if we include the signs of a charge, what will happen? If both the charges are positive, you will get a positive force. If both the charges are negative, you will get a negative force. If one charge is positive, the other charge is negative, you will get a, sorry, if both the charge is negative, you will again get a positive force. You didn't understand? Okay, let me show you. See, we know that it is directly proportional to Q1 multiplied by Q2, right? If both the charges are positive, what ends up happening? Positive multiplied by positive will give you a positive force. Negative multiplied by negative will again give you a positive force. But positive multiplied by negative gives you what? A negative force. So a positive force represents repulsion. A positive force represents repulsion, but a negative force represents attraction. So, this is how we can figure out the direction of force. This is how we can figure out the direction of force in charged objects, even though we don't have any charge based, direction based quantities in the force. Okay, now, where were we? Yeah, okay. So, take the positive direction to be from A to B in figure 8. This is from the left to the right, the positive x direction. Begin with both charges A and charge B positive. When two positive charges are multiplied together, the resultant sign of the force acting on B due to the charge A is also positive. This means that the direction of force B will be assigned the positive direction from charge A to B. In other words, left to right. This agrees because charge B is repelled. Now, just all this blah 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 nonsense is not required. Just Remember that if the force is positive, there will be repulsion. If the force is negative, there will be attraction. Understood? Now, when one of the charges is positive and the other charge is negative, the product becomes negative, and then you get an attractive force. That's it. Okay, you get an attractive force. The force on charge B due to charge A is now to the left. Again, this agrees with what we have expected. That is the charge attracted because they have of what charges opposite signs. Understood? Now, what is we have to learn about what the value of k is, how we got the value of k as 9 into 10 raised power 9. We have to understand that. Another way to quote the constant is k is equal to 1 upon 4 pi epsilon naught, where 4 pi is a constant, right? 4 pi are just mathematical terms, they're constant. But we have one small thing here, this epsilon naught. Okay, the epsilon naught is known as the permittivity of free space, is a historical term for vacuum. The 4 pi is added to rationalize the electric and magnetic equation. In other words, to give them a similar shape and to retain an important relationship between them. See topic D3, page 550. We will do that later. Okay, now the equation becomes F is equal to Q1 Q2 upon 4 pi epsilon naught R square if you apply the full value of K. Now, this means that epsilon naught takes in a value of 8.8 into 10 to the power minus 12 coulomb square Newton per meter square. Okay, coulomb square per Newton meter square. Coulomb square per Newton meter square, that becomes the unit of epsilon naught. It becomes the unit of epsilon naught. Understood? Okay, the equation as it stands applies only to charges that are in vacuum. When the charges are immersed in different media, say air or water, then the value of the epsilon naught or the permittivity is different. It is used to amend the equation slightly. K becomes equal to 1 upon 4 pi epsilon. Epsilon naught would mean that the medium is a vacuum. Okay, but if the medium is no longer a vacuum, then the O, epsilon naught, the O changes and you are left with epsilon, where epsilon represents the permittivity of the medium in which the charges are kept. Okay, now as the O subscript in epsilon naught is only used for the case of vacuum. For example, the permittivity of water is 7.8 into 10 raised power minus 10 coulomb square per Newton meter square, and the permittivity of air is 8.85 into 10 raised power minus 12 coulomb square per Newton meter square. The value of permittivity of air is so close to that of vacuum that we generally consider the permittivity of free space and vacuum to be equal. Okay, we consider them both to be equal because look at this. You have 8.854 into 10 raised power minus 12 and 8.849. 8.8549 and 54, they are approximately the same, almost the same. So we can consider them to be one and the same. Understood? Okay. So the table gives permittivity values for some different materials. Paper has a permittivity of 34 into 10 raised power minus 12. Rubber has 62. Water has 779. Graphite has 106. And diamond has 71. Okay. So, did you understand the logic behind this? Okay. Now, worked example number 2. What is worked example number 2? Let's see. Hmm. 2-point charges of plus 10 nanocoulombs and minus 10 nanocoulombs are in air are separated by a distance of 15 meters. Calculate the force acting between the two charges. Easy, right? So you can use F is equal to what? K Q1 Q2 upon R squared. So you know the value of K to be 9 into 10 to the power 9. You can consider it 8.99 can be simply written as 9. Okay, Akshay, 8.99 can simply be written as 9. 9 into 10 is power 9 multiplied by 10 into 10 into minus 1 into 10 to the power of minus what, 18. Okay, or you can say 1 into 10 is power minus 19. Sorry, 1 into 10 is power minus 16 upon 15 millimeters. The distance should be in meters. So 15 into 10 raised power minus 3. Okay, the whole square. Now, when you use that formula, you will get the answer to be minus 4 into 10 raised power minus 3 newtons. Okay, all you have to do is plug in the values, use the calculator, find the answer. Understood? Simple, right? Comment on whether this force can lift a small piece of paper about 2 millimeter multiplied by 2 millimeter in area. Okay, now have they given us the density or nothing? No, we have to assume everything. Okay, so a sheet of paper, thin A4 sheet of paper of dimensions 210 millimeters by 297 millimeter has a mass of about 2 grams. So the small area of paper has a mass of about 1.3 into 10 to the power minus 7 kgs, and therefore a weight of 1.3 into 10 raised power minus 6 newtons. Now, how did we get the weight? You've calculated the mass, and weight can be calculated by using the formula mg. Okay, mg, right? Now, if you have mg calculated, then all you have to do is check whether this force, this force is bigger than the weight of this object. It is obviously bigger than the weight of this object, right? The force is 10 to the power minus 3, whereas the weight is 10 to the power minus 6. So obviously the force, the electrostatic force wins. This electrostatic force will be able to attract the piece of paper and make it come towards itself. Okay, so this weight is overpowered by the force. This weight is overpowered by the electrostatic force of attraction. Understood? Next, 2-point charges of magnitude plus 5 microcoulomb and plus 3 microcoulomb are placed 1.5 meters apart in a liquid that has a permittivity of 2.3 into 10 raised power minus 11. Calculate the force between the point charges. Now you cannot use 9 into 10 raised power 9, because 9 into 10 raised power 9 value is only useful in the case of epsilon naught. Here what do you have to do? Epsilon naught is the only value in the case of 9 into 10 is power 9. Here you have to do the whole calculation like this. Force is equal to 1 upon 4 pi epsilon q1 q2 upon r square. So the force becomes 1 upon 4 pi into 2.3 into 10 to the power minus 11 mul- multiplied by 5 into 10 to the power minus 6 multiplied by 3 into 10 to the power of minus 6 upon r square, that is upon 1.5 the whole square. Clear? So if you put this in the calculator, you will get the answer. Any doubts in this question, Akshay? Okay. Okay. Permittivity means the ability for the electric field lines to flow through it. Okay, how well is it allowing the electric field lines? We are going to understand this later. When we study electric field lines, we will understand what they are. Okay, how well are they allowing the field lines to pass through the medium? Okay, now I'll explain this to you in a little bit of small logic. Now, did we see anything like that in the case of gravity? Gravity is not affected by the medium at all. Gravity is not affected by the medium at all, but electrostatic forces are affected by the medium. And if the medium permits The medium has to permit the flow of electric field lines through it. Okay, if if they are able to permit well, then what happens, the force will become stronger because the field that is flowing, the electric field lines that are flowing through them will become what, they will become larger. Okay, they will become larger. So one thing is that is clear is, if the permittivity, if the value of permittivity increases, then what happens, the denominator increases. 1 upon 4 pi epsilon naught is part of the denominator, right? If the permittivity increases, then what happens, that the denominator also increases. Therefore what ends up happening, the force between the two will start to decrease. Okay, so I'll do one thing. I'll explain you permittivity in more detail in next class. Okay, when we will learn more about electric field and everything. Okay, now, so we have finished. So we'll practice these questions. This practice questions now. We'll do them in the next class. This topic, Drupad, Akshay, this topic, the electric field, is where we will understand majority of what is happening. How is the field? How is a non-contact force able to exert its presence on other charged objects or neutral objects? It is because it is able to create field lines. Once we understand the concept of field lines, rest of the topic becomes very, very clear. Understood? Okay, clear? Okay, so we will stop the class for now at this point, and we'll continue this in tomorrow's class. Just one second. So, if you like my video, if you like the way I teach, if you like my explanations really, really well, so then please like, share, and subscribe my channel. Okay, and I'll meet you in the next video. Thank you.